Hey everyone, and welcome. Today we are getting our hands dirty and building something from the ground up, the binary tree. And look, forget any scary computer science jargon you might have heard. Just think of this as one of the most elegant, powerful ways to organize information ever created. So let's get building. So you might be wondering, why do we even need trees in the first place? Well, if you've ever had to find one specific thing in a gigantic, messy list, you know the pain, right? Arrays and lists, they can be super slow to search, and they're not really great for showing how things are connected in a hierarchy. But trees, oh, they are literally designed for speed and structure. They are the hero we need for this exact problem. Here's our game plan for the next few minutes. First, we'll go from simple links to full-on branches. Then, we'll cover the anatomy of a tree, all the lingo. After that, we'll get into the art of traversal. And finally, we'll see why any of this actually matters in the real world. Okay, first things first. Every great building, every great structure starts with a single basic blueprint. Let's take a look at ours. So, at its absolute core, a tree is really just like a family tree. It's that simple. You've got pieces of data connected to other pieces of data. A parent can have children, but, and this is key, a child can't also be its own grandparent. There are no weird, confusing circles. It's just a clean, top-down structure. Now, we're going to zoom in a little. We are focusing on a very special type of tree called a binary tree. And the rule here is incredibly simple. Each piece of data, which from now on we're going to call a node, can have 0, 1, or the absolute most 2 children. And these children have specific spots, a left child and a right child. That's it. That's the main rule. And here it is. This is the blueprint written out in code. You can think of this little struct node as the DNA for every single block in our tree. It's so elegant. Each one holds a piece of data, in this case just a number, and then it has 2, well, think of them as signposts. One that can point to a node on its left, and one that can point to a node on its right. All right, we've got our blueprint. Now it's time to start assembling the pieces and learn the official lingo. This is the vocabulary we're going to need to talk about this thing we're building. First up, the node. This is as basic as it gets. It's the fundamental building block. It's just the box, the container, that holds one piece of information inside our tree. Now, every tree has to start somewhere, right? We call that starting point the root. It's the one single node at the very top that doesn't have a parent. Everything else in the entire tree branches out from here. And just like that family tree we talked about, this relationship is everything. A parent is any node that has connections leading down to other nodes. And what do we call those nodes below it? Yep, it's children. So what about the very ends of the branches? Where does it all stop? Well, we call those leaf nodes. These are the nodes at the very bottom of the tree that have no children of their own. They are, quite literally, the end of the line for that branch. Okay, so we have our structure. We know what to call all the parts, but how do we actually use it? This brings us to what I think is the real superpower of trees, how to navigate them in a really smart, systematic way. So here's the big question. You've built this thing. It could have hundreds, thousands, even millions of nodes. How do you write a program that can walk through and visit every single one without missing any, and without visiting the same one twice? The answer to that puzzle is called traversal. It's just a formal name for the process of walking through the tree and visiting every single node exactly one time. It's a core operation. I mean, if you want to find something or print everything or even delete the tree, you have to traverse it first. So, our first method is called in-order traversal. The pattern is always the same. Go left, visit the root, then go right. And here's where the magic happens. If your tree is organized in a special way, with smaller values to the left and larger ones to the right, this traversal method will naturally print out all the data in perfect sorted order. It's so cool! Next up is pre-order traversal. Notice the difference? Here, you visit the root first, then you go left, and then you go right. This method is absolutely perfect for when you need to make a copy or a duplicate of a tree. It makes sense, right? You create the parent node first to establish the structure, and then you build out its left and right sides. It's a perfect way to make a replica. And our final method is post-order traversal. The pattern here is go all the way left, go all the way right, and then visit the root last. Why last? Well, this is incredibly useful for deleting a tree. Think about it. You have to safely get rid of the children before you can get rid of their parent. And this parent-last order guarantees that happens perfectly every time. Now, those three methods we just saw, in-order, pre-order, and post-order, are all part of a bigger strategy called depth-first search, or DFS. And it does what it says. It dives deep down one branch all the way to the end before it backs up. The alternative is called breadth-first search, or BFS, and the analogy here is perfect. It explores the tree level by level, kind of like ripples spreading out in a pond. Okay, we have covered a lot. We've got the blueprint, the anatomy, the different ways to navigate it. But let's ask the big question. Why did we go to all this trouble? Let's zoom out and see where these amazing structures are actually working behind the scenes in our everyday lives. This is why it all matters. Turns out trees are everywhere. The folder structure on your computer, folders inside of folders, that's a tree. The crazy fast way a database can find your information out of millions of records, that's thanks to tree-based indexing. AI models use decision trees to make choices, and the very structure of the web pages you're browsing is understood by your browser using, you guessed it, trees. So how fast is this stuff? In geek speak, traversal is O of N. But forget the jargon. Here's what that really means in plain English. The time it takes to visit every node is directly tied to how many nodes there are. If you double the nodes, you pretty much double the time. It's a really efficient and predictable pace, which is exactly what you want. So we've got this incredible structure that gives us both amazing speed and a natural hierarchy. But there's a catch. What happens if our tree grows all weird and unbalanced, and it ends up looking like just one long lopsided branch? Well, then it starts to look and act just like one of those slow lists we were trying to avoid in the first place. And solving that problem, well, that's a perfect gateway to our next topic, self-balancing trees.